What is the probability of landing in the circular region, given that you're equally likely to land anywhere within the entire square? This is an example of an easy probability problem, which has a nice closed-form solution, pi over 4. Now, if we were to throw a needle of some fixed length on the square board, what is the probability that the needle lands entirely inside the circle, given that at least one end of the needle is inside the board? This is significantly harder, and you need to set up some complicated integral that barely fits in a single page. Now, what if you're actually tossing the needle on a magnetic board at a distance? There are so many more things to consider. For example, the horizontal and the vertical landing position are not independent due to the anatomy of our shoulder joint. To make the problem a bit simpler, let's ignore the horizontal motion. Then, maybe we could simplify the problem down to just 3 variables. The angle of the throw, the initial speed of the throw, and the height of the thrower. And even that is still too many things to consider, so let's keep the height and the speed constant. And let's assume that the variation in the angle is normally distributed with some truncation, meaning we only want to consider the case where the object actually lands on the board. Even with this much simplification, it still is impossible to find the exact shape of the distribution, so I can only get an approximate shape using computer random number generator. Real-world problems can get really complicated. For example, if we account for turbulence, randomness can get much less predictable. In general, typical probability problems can be split into 2 types. Ones where exact distribution in play is unknown, and different variables may be correlated but we don't exactly know how. An average person would call this a probability problem because we're dealing with chances and odds. But in formal definition, these are in the domain of statistics and data science. As per proper probability problems, we know the exact mathematical statement of the problem, and we know the distribution in play. But even then, the problem could get really hard and impossible to solve analytically, such as calculating the expected time for a particle in Brownian motion to escape the maze. So we use computer random number generators to simulate the experiments to approximate the answer. And such technique is called the Monte Carlo method. But in order to use such technique, we need to be able to generate random numbers of any distribution we need. So how do we do that? The probability distribution that we are most familiar with is the normal distribution. In particular, this is the normal distribution with the mean of 100 and the standard deviation of 15. So what even is a probability distribution? We actually don't have an answer for that right now. Instead, we can define a random variable capital X that is normally distributed. X can take on any real number value just like a regular variable, but what differentiates it is that we can calculate the probability on it. And the probability that a normal random variable is sitting in between plus and minus 1 deviation is roughly 68%. This is the working definition we will be using for this video, but as for a more formal definition of a random variable, I made another video on the topic and it's in the description below. And as for what a probability distribution is, it is the measure of probability assigned on the variable. But what's really useful is the random variable and the shape of the distribution. And the function that represents the shape is called the probability density function, which we typically call the PDF. And the PDF of a normal random variable is the bell curve. PDF naturally is an object that makes sense under an integral with respect to a dummy variable little x in order to spit out probability. Next useful function is the cumulative distribution function, or CDF, which can be defined as the integral of PDF from -infinity to the dummy variable. And this function spits out the total probability of the left tail of any value x. That's all the prerequisite definition we need, so can we try it for another distribution? Uniform distribution on an interval a to b is a probability distribution where each value from a to b is equally likely to show up. So the PDF has height of 1 over the length of the interval, so that the area under the curve, or the total probability, is exactly 1, times the indicator function from a to b, which simply spits out 1 from a to b. Then, the cumulative distribution function is a piecewise linear function that is increasing in the middle section. Now, just like how normal distributions have a standard version, which is centered at 0 and has standard deviation of 1, We will call the uniform distribution from 0 to 1 the standard uniform distribution. Notice how the CDF was increasing from 0 to 1 continuously, and same for the normal distribution. So these two are examples of continuous distributions. And we're also familiar with many non-continuous distributions. For example, the discrete uniform distribution from 1 to 4 randomly spits out any integer from 1 through 4 with equal chance. This is an example of a discrete distribution, so it has something called a probability mass function as opposed to a density function. And the probability of getting each value is 1/4. Despite not having a density, cumulative distribution function does exist, which is a piecewise constant function that goes up at each values that have non-zero probability. What if the distribution is neither continuous nor discrete? Suppose this is the CDF of some probability distribution. The CDF has discontinuities at 1 and 3, so it's not a continuous distribution. And it's not going up in discrete steps, so it's not a discrete distribution either. So the probability has both point masses as well as a density. As per recovering the density of the continuous part, we can take the derivative of the CDF where we can. And as per the discrete point masses, we can represent them as infinite spikes with zero thickness. And these spikes can be constructed using the Dirac delta function. So technically, neither the density nor the mass function exist, but using the notion of generalized functions, we can artificially construct the density function. In general, it can be proven that every probability distribution is made of discrete part and the continuous part, just like the example above. And this is a version of the Lebesgue decomposition theorem. Furthermore, a continuous distribution can be further decomposed into absolutely continuous part and singular continuous part. As per what these are, an absolutely continuous function plays nicely with derivatives and integrals, so you can take the derivative of the CDF to get the PDF and the integral to get the CDF again. And in order to allow the discrete part to play nicely with calculus, we had to make some patchwork with Dirac delta functions. As for the singular part, they don't play nicely with calculus either, but to be honest, they are way too abstract to be of any relevance in this video, so we will use continuous synonymously with absolutely continuous. So we looked at several different distributions, continuous, discrete, and mixed. And the central idea behind creating random number generators of any distribution relies on transformations of random variables. So let's start with some basic intuitions. Let x be a random variable, which is uniformly distributed from -1/2 to +1/2. Then how is another random variable y distributed, given that y is x plus 1.5? Y would simply take all the allowed values of x and adds 1.5 to it. And all the same probability rules apply to y as long as you add 1.5 to x. So it's not too surprising that y is just 1.5 step shifted version of x. Now, what about y equals 2 times x? This time, we scale x by 2, so y can take on any value from -1 to +1. But we have stretched the distribution horizontally, so the area is now 2, so we would have to scale down the graph by 1/2. If we multiply by a negative number, the density would reflect about the vertical axis. But since our original distribution had an even symmetry, the density function would look the same. So combining translation and scaling, we can transform the standard normal distribution to create every normal distribution with any mean and standard deviation. For the context of this video, we will call such a linear transformation. Next easiest case we will look at are piecewise linear transformations like absolute value of x. For all positive values of x, the transformation doesn't do anything. And as per any negative value, it gets reflected to become a positive value, and the densities add together. In general, if the transformation of random variable is not 1-to-1, we will see some probability densities add together. So if we apply absolute value on a normal random variable, then negative values just flip over to the positive, and the density on the right side just doubles. Now, what if the piecewise linear transformation has a constant portion? For any positive values of x, it is the identity transformation, so it is untouched. But for any negative values of x, it is mapped to -1. So entire 1/2 of the probability just gets mapped to a single point mass at -1. So we looked at every possible cases we can make with piecewise linear transformations, including many to one and piecewise constant. So our next order of business is nonlinear transformation. So let's take x to be a standard uniform random variable and y and z to be x squared and square root of x respectively. We can sample a whole bunch of points that x can take, and 0 squared is 0, and 1 squared is 1. So y should be a distribution that ranges from 0 to 1 as well. Now, if we map all the other samples, more points are gathered around the left tail, so the distribution is probably heavier on the left side. Now, if we do the same for the square root, the distribution is probably right-leaning. So, if we use a standard uniform random number generator, then square or square root each value to create these two histograms, then we can see that the experiment confirms our suspicion. So, what is going on? We will come back to these two transformations later. First, I will introduce the textbook method, which is how it's typically taught in a classroom. Then we will see what it geometrically means. X is a standard normal random variable, and we want to find how y is distributed. So we first start off with the CDF of y, which by definition is the probability that big Y is less than or equal to the dummy variable little y. Next, y is equal to x squared. Then we can turn this into a compound inequality that is solved for x. Now, the probability of the central region can be split into the probability up to the right value minus the probability up to the left value. So we can split up the expression. And since the continuous distribution have no point masses, we can just turn the less than into less than or equal to. And from here, we'll just choose to be sloppy with our inequality unless there is a discrete part. So we got the CDF of y written as two terms that are CDF of x. So all the key steps are finished, but maybe we can abuse the symmetry of this very specific distribution to simplify it. The left tail and the right tail should have the same probability. And the probability of the right tail should be 1 minus the probability up to the square root of y. So we can combine like terms, then the CDF of y is simplified in terms of CDF of x. As for what they are, neither the CDF of y nor x can be expressed in closed form in terms of elementary functions, but at least we can find the PDF. We will first differentiate the left side and the right side, then we have to apply chain rule. Then, since we know what the PDF of the standard normal distribution is, we can just plug in the square root of y. Then we can move the negative power to the bottom. And we have the PDF of y. This distribution is called a chi-square distribution with 1 degree of freedom. In general, we can use the exact same technique to derive the PDF and CDF of any transform distribution. So what does this geometrically mean? Earlier, we naively stretched our distribution horizontally by a factor of 2, but in order to preserve the probability, the height had to be scaled down by a factor of 1/2. So the probability between any 2 points A and B on the left should be same as the probability of landing in between 2A and 2B on the right side. So same story should hold for any transformation. Now, for the sake of illustration, let's assume that g is 1-to-1 increasing function. Then each point on the left side, which we can use little x, should map to some point y on the right side. Then, just like before, let's falsely assume that the height of the function is unchanged from the left side. These heights can be described as the left function evaluated at x, or equivalently, g inverse of y. But what's not true is simply attaching dx and dy on both sides. Since we scaled our graph horizontally, we have to counter-adjust the height as well. So how much is the scale factor? If we take an infinitesimal length on the left side, the horizontal scale factor is the derivative of the transformation at that point. And this is exactly how much we want to divide the height by at each point. Now, algebraically, g prime of x dx is equal to dy. Now we can isolate dx and use the inverse function theorem. Now we can properly multiply by dx on both sides, and this should look quite familiar. The inverse scale factor naturally pops out as the consequence of integration by substitution. So we have a formula for the PDF of y whenever the transformation is 1-to-1 increasing. So what if the transformation is decreasing? Can't we just use the same formula? In regular calculus, if we substitute x with negative u, then the scale factor comes out to be negative. So the scale factor accounts for the fact that there has been a reflection. So the integrand becomes negative, but also the limits of the integration changes ordering, so the integral is the same. But in probability theory, we need the density to be non-negative, and we always integrate from left to right to calculate probability. So we only really care about the absolute scale factor. So we now have a formula that works for both increasing and decreasing transformations. Now, what if the transformation is piecewise monotonic? If you recall from the absolute value case, we have to stack some densities since the transformation is many to one. So we will make some branch cuts on the transformation, then sum over each different branches of the inverse. Now, back to these problems. The PDF of the standard uniform distribution is 1. So the PDF of y is the PDF of x of square root of x times the derivative of square root of x. But the PDF of x is 1. And similarly, the PDF of z is the derivative of x squared. So we now know how to transform any random variables. Now, in order to create random number generators, we have to take a step away from calculus and do some number theory. So let x naught be 2, and define the recursive step so that the next number is 5 times the previous number plus 3, then divide by 16 and get the remainder. If we apply the iteration on 2, we get 13. And we can keep going until we go back to where we started. Notice how each number from 0 through 15 shows up exactly once in a fairly unpredictable order. We are free to choose whatever number we start with, which we call the seed value. Now, if we change the multiplier to 7 and the increment to 4, then it gets horribly predictable, and some cycles even have a period length of 1. So it's important to choose good values of a and b for a given modulo m, and this is called the linear congruential generator. So what is a good choice of the modulus? Since we are typically using a base 2 machine to do our arithmetic, a power up 2 is a decent choice. And this is analogous to how taking a modulo of power up 10 is simply truncating higher digits. So for a computer, taking a modulo of power up 2 is simply truncating bits. As for a good choice of the multiplier, 1 is a poor choice since it makes the pattern way too predictable. And for the same reason, increment of 0 is a poor choice. Now, in order to construct a linear congruential generator that goes through every number, we need to satisfy 3 conditions. First, the increment has to be relatively prime to m. Second, for any prime factor p of m, a-1 must also be divisible by p. Lastly, if m is divisible by 4, then a-1 also must be divisible by 4. And these 3 conditions guarantees that the generator runs through every number, and this is called Hall-Dobel theorem. And if we impose the condition that m is a power of 2 greater than or equal to 8, then these 3 statements just simplify to 2 statements. First, b is odd, and second, a-1 is divisible by 4. Now, using the linear congruential generator, we can construct a generator for the standard uniform distribution. Choose a large power of 2 for the modulo, then for a well-chosen pair of a and b, it will run through each number in a fairly random order. If we divide each of these numbers by m, then each of these numbers go from 0 to some number barely less than 1. If we take the mean of these numbers, we get 1/2 times m-1 over m. And if we work over 32 bits, which is a common choice for computer arithmetic, there is a very slight bias towards the left. So why don't we just divide by m-1 instead? Well, the problem with that is division by any number can get pretty costly. But division by a power of 2 is simply shifting bits, just like how division by a power of 10 is shifting digits. The default random number generator for most programming languages generate a uniform distribution from 0 inclusive to 1 exclusive. And the left bias really is there to save the computational cost of division. I introduced linear congruential generator, which was at one point the most popular generator, but Mersenne Twister invented in 1997 is the generator of choice today. But it is significantly more complicated than the linear congruential generator. So we know how to generate standard uniform distribution. So if we can find a way to transform it to any distribution we want, then we can construct any random number generator. The case you most likely have encountered in your very first programming class is to create a discrete generator from the standard uniform distribution. For example, let's take a look at this distribution, which represents an unfair four-sided die, such that the probability of getting 1 is 1/2. Then, if the uniform random variable is less than 0.5, then we would write the function to output 1. Then the next interval of length 0.3, so 0.5 to 0.8, we would output 2. And next two intervals of length 0.1 each, we would output 3 and 4 respectively. And we honestly did not invoke any advanced mathematics, since finding a partial area of a unit square is such an easy task. And soon, we will see how nice the standard uniform distribution is. If x is the standard normal variable, how do we transform it from the standard uniform? The most important property of a standard uniform distribution is that the CDF is the identity function on the domain that the probability changes from 0 to 1. CDF of x is 1-to-1 increasing function, which can be written in a closed form in terms of the error function if you're curious. So it is invertible, and the inverse function has the domain 0 to 1. Since the CDF of u is the identity function, it is the composition of any invertible function and its inverse. And this by definition is the probability that the random variable x is less than or equal to the fx inverse of little x. Which is same as the probability that fx of big X is less than or equal to little x. And this by definition is the CDF of fx of x. So u and fx of x must be the same distribution. Nowhere in this algebraic proof did we assume that x was actually normal, just that the CDF of x had to be 1-to-1. And as long as that is true, we can apply the inverse function on both sides to get the transform from u to x. Now, what does this geometrically mean? Let's take a look at the simplest transform to illustrate the point, where the transform is horizontal stretched by a factor of 2. If you remember what happens to the density, it had to be scaled down by 1/2. But once you integrate the density, there is a horizontal scaling but no vertical scaling. Algebraically, when we did the change of variables on the density, we had to horizontally scale up by multiplying 1/2 in the function argument, but also multiply by 1/2 to vertically scale down. But once we integrate both sides, the extra chain disappears, so the CDF only scales horizontally. Now, same idea for any non-linear transformation g. In order to horizontally scale by g, we apply the inverse function of g. And since the PDF of the standard uniform is the identity, we just get the g inverse of x. Now, let's go back to x being the standard normal distribution. And let's start with the CDF of u, and we can sample some points to see where it goes. If we scale the values horizontally by applying the inverse CDF of x on each input variable, then the curve gets stretched out to infinity, giving us the original CDF of x. So this works, as long as the CDF was 1-to-1 to begin with. But what if that is not the case? The density has some point masses, and there are regions of 0 probability, so the CDF has discontinuities as well as constant region. So the CDF is definitely not invertible. So we have to introduce a concept called the generalized inverse, which has this formal definition. But it's quite complicated, so let's try to get an informal intuition behind this. First, let's connect all the jump discontinuities with straight lines. Then, once we flip the role of domain and range, this is essentially what the generalized inverse is. Let's try this on the discrete probability distribution we saw earlier. We can plot the CDF of x, but the vertical axis as the domain. Next, we can connect all the lines. And for ease of understanding what this function really is doing, let's remove all the vertical lines and color code the horizontal lines. And this function really gives us what we originally wanted, a function that outputs 1 for the first 1/2 of the region, 2 for the next 0.3 of the region, and so on. So, using the notion of generalized inverse, we can get any distribution from the uniform distribution. But going the other way is not always possible. And it's only possible if x is purely continuous. Intuitively, we can turn a uniform distribution to a coin throw, but by doing so, we lose a lot of information. And the process is non-reversible. There is no way to get back a continuum of information from a single coin throw. Then, how do we turn any continuous random variable x to any random variable y? The generators we have talked about earlier, like the linear congruential generator and Mersenne twistors, are examples of pseudo-random generators. And that is because the sequence they generate are deterministic and they only appear random. But sometimes we do need true randomness. For example, if you're running an online gambling platform, if you used a pseudo-random number generator, then someone could reverse engineer the sequence of past events to determine what is to come. And we typically capture true randomness from real life, such as voltage fluctuations and radioactivities. At Cloudflare, a cybersecurity company, they use random movements of lava lamps to generate randomness. And more likely than not, these real randomness probably is not uniformly distributed. So how do we go from non-uniform x to y? Well, we can first convert x to u, the common language of probability distributions. Then convert u to y. So we now can construct random number generators of any distribution.